Hello and welcome to some more questions on Hooke's law using the formula. So if we look at question 6 here, we've got a slightly more complicated situation. We've got an elastic string, length 10, modulus of elasticity 130. The ends are attached to fixed points A and B, which are at the same horizontal level, and a small stone is attached to the midpoint of the string and hangs in equilibrium. So we've got the force down here, which is the weight of the stone acting downwards. So the weight of the stone, do we know that? Yes, we're trying to show the mass of the stone is 3 kilograms. So we're going to call that force down there mg, and we're going to work out what m is, and we're hoping it's going to come out to 3. So we need to put in all the forces on the diagram. So we've got a tension in each string like that. We can treat it as 2 separate strings, each of length 5. So the natural length of one section of string is 5. The extension is therefore 1.5. And lambda, we're told, is 130. We also, because we're going to need to do some resolving in a minute, we need to know that angle there. So we need to say that cos theta is equal to 2.5 over 6.5. And we'll use that later on. So let's apply Hooke's law to this situation. We've got the tension in the string is equal to lambda x over L, which is equal to 130 multiplied by 1.5 divided by 5, and that gives me 39 newtons. So the tension in the string is 39 newtons. We're now going to resolve vertically. So resolving this force T vertically, we've got T cos theta. That's the vertical component of T. And we've got 2 of those because there's 2 strings pulling upwards. And that must be equal to mg, because that's the force acting down and the system is in equilibrium. So now substituting the values we've got, 2 multiplied by the tension in the string, which is 39, multiplied by cos theta here, which we can put as 2.5 over 6.5, or you could work out the actual angle, but we can just fill that in there, equals, now it asks us to use G as 10, so we're going to say 10m. And when I work this out, I get m is 3 kilograms, which is what was needed. So we've shown that the mass of the stone is 3 kilograms. Moving on to the next question. Yeah, we've got quite a complicated situation here. We've got a rod AB, length 2 meters, and it's got a mass of 10 kilograms. It's freely hinged at B. Then we've got an elastic string, modulus 100 newtons, one end attached to A, and the other end is attached to a fixed point O, which is in the same vertical plane as the rod. So think of this as a rod coming out of a wall, and then you've got an elastic string holding it up, because otherwise this rod would fall downwards. It's horizontal, the system is horizontal, and it's in equilibrium. O to A is equal to 3, and the angle OAB is 150 degrees. So the first thing we need to do is put in all the forces that are acting. So we're going to have a force down here of 10g, because that is the mass of the rod multiplied by g. We're going to have a tension in the string going up there. It's probably useful to know that that angle there is 60 degrees, because we're going to do some resolving later on. What's happening at the hinge? Well, there must be forces acting at the hinge, because if the system is in equilibrium, at the moment, if there was no forces acting at the hinge, these 2 forces can't be in equilibrium, because this has a horizontal component and something must be matching that. So there must be a horizontal force that way, and there will be a horizontal force, a vertical force in that direction. Might possibly be, this force might possibly be going up. If that's the case, it'll come out as negative in your working. So don't worry about that too much. So we've got all the forces on the diagram, and we want to find the tension in the string. So what we're going to do first of all, we need to think, could we find the tension in the string using Hooke's law? Not yet, because we don't have enough information. We know that this is equal to 3 meters, but we don't know the natural length of the string. So that's going to make it hard to work out using Hooke's law to start off with. But what we can do is we can take moments about the hinge. That's often something you do in mechanics questions. So if you take moments about here, then there is no, we don't need to include these forces, and that makes life a lot easier. So taking moments about B, which is where the hinge is, these have no moment. So then we've got 10G multiplied by 1, going around this way. Then you need to think of the 2 components of this. So you've got one component in this direction. That will have no moment through B because it acts through the point of turning. Resolve this force in this direction. So we've got T cos theta multiplied by 2. So minus T cos theta multiplied by 2. And that must be equal to 0 because the system is in equilibrium. So this gives me T. Now cos theta, cos of 60 is going to be a half times 2. So that comes out to be T is equal to 10 times 9.8, which is 98 newtons. So now we know the tension of the string. So now we can use Hooke's law. So Hooke's law is that the tension is equal to lambda x over L, and we fill in the values we know. So we've got 98 for the tension. Lambda is equal to 200 because we are told that up here. The extension is what we're trying to find. And we know that this is 3 meters. So the natural length of the string is 3 minus x. So it might have been a good idea to define my x and say here x is the extension of the string. So this is giving me a straightforward equation to solve. I'm going to say 98 multiplied by 3 minus x is equal to 200x. And solving that, I get that x is equal to 0.9866. The length of the string, which is what we're asked to find, is going to be 3 minus x, which is equal to 2.01 meters. So this is an example of a question where you are expected to use some of your single maths mechanics. So just watch out for those questions. So you now need to work through the rest of exercise 3A, questions 7 to 11.